Okay, so my name is Paul KB0p. I'm located in Green Bay, Wisconsin. Call letters KB0p, and this is my presentation on wire antenna basics. Keep in mind that this is just a basic presentation. After the presentation is over, we'll open up for questions and comments, and then we can discuss some things in further detail. So we're going to talk about the dipole antenna. So the most common dipole antenna in our households that we may recognize is the TV rabbit ears. This presentation will provide a brief introduction to simple wire antennas for use on HF frequencies in amateur radio. At the end of this presentation, the participant will be able to identify the components of a dipole antenna, explain the purpose of a balun and a choke, use the formulas to build a wire antenna, convey the construction methods of a G5RV and an off-center fed antenna. I'm going to talk about both of those briefly, and then build an effective wire antenna. And presentation outlines. So we're going to talk about these different things in this order. And we're going to start with some real basic definitions, that terms I'm going to use throughout the presentation. We're going to talk about the anatomy of a ham radio dipole antenna. What is a dipole antenna? What is a balun and a choke? Wire antenna formulas. We're going to visit two common wire antennas, and the two we're going to cover real briefly is the G5RV and the off-center fed. Then we're going to go into building your own wire antenna, conclusion, and then afterwards, like I just mentioned, we'll open up for discussion and questions. So let's cover a couple simple definitions. So first of all, antenna. So what is an antenna? An antenna is a device or circuit, if you will, that radiates a radio signal into the air. Basically, that's all it is. What is a feed line? Well, a feed line is a line used to connect the antenna to the radio. The difference between an antenna and a feed line is the antenna actually radiates a signal. The feed line is not supposed to radiate the signal. The feed line is a means of getting the signal from the radio to the antenna. So the feed line is not supposed to radiate a signal. Keep that in mind. Feed point. So feed point is the point on the antenna that connects to the feed line. So wherever you connect the feed line to the antenna, that connection point is known as the feed point. And resonance. Resonance is just another word for tuned. A resonant antenna or resonant antennas are tuned to a specific frequency. So when an antenna is in resonance, it's actually tuned to a particular frequency, and it's in resonance at that frequency. So resonance is just a different word we're going to use for a tuned circuit or tuned antenna. So the anatomy of a ham radio dipole antenna. So we'll just hang out here a little bit, discuss this. So this is just a simple diagram of a dipole antenna. So you'll notice, can you see my mouse moving around here? Hopefully you can. But you'll notice that we have a couple legs here. So we have two legs or two pieces of wire. The wire's fed in the center, and then we feed the wire with a feed line. So the antenna is fed with a feed line. We also have a device here that we're going to talk about. It's called the balun, and the location of the balun in this drawing is right at the feed point of the antenna, where the feed line connects to the antenna itself. And then at the bottom here, I drew in a little choke, and we'll also talk about what the purpose of the choke is as well. Then we have our insulators, and the insulators can be made of most, anything. I mean, a piece of PVC pipe, a piece of glass. You can buy these ceramic insulators online, these plastic insulators online. There's so many different options there, just as long as it's a material that does not conduct electricity. And then a good piece of rope to support the antenna in the air, perhaps between two trees. Another thing I want to point out here in this drawing, you'll notice here at the top, is the total length of this antenna is a half a wavelength. Now, what do I mean by half wavelength? Well, half wavelength is at the frequency the antenna is designed for. So every frequency in ham radio has a wavelength. For instance, when we're down on 80 meters, that would be the 80 meter band would start at 3.5 megahertz. So that's the 80 meter band. The 40 meter band would be at 7 megahertz. 20 meter band would be at 14 megahertz. So when I say it's a half a wavelength, and if we were building an antenna for 80 meters, a half a wavelength of 80 meters is 40 meters. So the antenna would actually be 40 meters long for 80 meters. If we're building an antenna for 40 meters, a half a wavelength, a piece of wire would actually be 20 meters long. Okay, so that's what we're referring to as half a wavelength. 2 meters, if you were building a dipole for 2 meters, for example, that total length of that dipole would be 1 meter long. All right, so we got to define a couple other things here. When we look at this picture, maybe a couple questions come up. First of all, what is a dipole antenna? Why is it called a dipole? What is a balun and what is a choke? So we're going to go into that here next. So first of all, we'll do these in order. What is a dipole antenna? So a dipole antenna is an antenna that consists of two, the word di, two equal lengths of wire, or two equal lengths or two equal poles. A dipole antenna is constructed with a half wavelength of wire at the frequency that we're designing the antenna for. And then this wire is cut in half and is connected to the feed line at the exact center. So if we take a half a wavelength of wire and we feed that half wavelength of wire exactly in the center, we're going to have equal lengths of wire on each side of the feed point. And that is called a dipole. A dipole is two equal poles. So by definition, a dipole antenna is fed in the center. All right. You can see here I have the two equal lengths of a wire, one on each side, and I also show the feed line in the center point. So then, just to summarize this whole slide, a dipole antenna is a half wavelength piece of wire. The wire is cut in half. And when you take a half wavelength piece of wire, cut it in half, each leg is now a quarter wavelength long, equally. And then the feed point is at the center. So those are the three main points of a dipole antenna. Half wavelength piece of wire, wire's cut in half, and the feed point is right at the center. So now I have a couple more questions. Why are we feeding? First of all, why are we using a half wavelength piece of wire? And then why is this antenna fed at the center? Why is it half wavelength piece of wire? Well, that's just the way nature is. There's formulas to calculate and show how this works and why it's a half wavelength piece of wire. But the way nature is, if you look at organs, you know, those large organs that you see in mega churches, you know, huge churches, the musical organs, I read that the tubes for those organs are in half wavelength lengths to make so the sound is resonant to the tubes and the sound comes out, you know, and sounds nice. Bagpipe drones, the drones sticking out of the back of the bagpipes, those are tubes that are tuned for best resonance. Radio antenna feed line demonstrates half wavelength patterns. So if I have a piece of feed line, like a piece of ladder line or a piece of coax, which we generally use for feed line and amateur radio, there's certain half wavelength patterns or characteristics that feed line demonstrates. And also radio antennas are resonant at half wavelengths. And actually, and keep this in mind, this is why I have it highlighted in red, radio antennas are resonant at a half wavelengths. Again, we talked about resonance. What is resonance? That means that the antenna is tuned to that particular frequency. So the antenna is resonant at a half wavelength. And as a matter of fact, it's resonant at odd multiples of half wavelengths. So 1 half, 3 halves, 5 halves, 7 halves, and so on and so forth. There's a reason why I'm bringing that up. And I'll point that out here later when we start talking about the G5RV antenna. Okay, why is the dipole fed in the center? Well, if you take a half wavelength piece of wire cut at whatever frequency you're operating at, right at the center of that wire, quarter wavelength in on either side, which would be right here at the center, the voltage point at that point is very low. And as a result, the impedance of that point is also very low. So the reason dipole antennas are fed in the center is because that is the low impedance point. And our feed line, like I'll pick coax for instance, coax is a 50 ohm feed line. And the feed point of a center of a dipole antenna, again, it depends on, the world's not perfect, so it depends on how close it is to the ground, the angle that it's sloped, things like that can vary anywhere from 50 to 70 ohms. And our feed line is also around 50 ohms. So that is a very good match for our feed line and antenna when the two come together, because they have relatively close and the same impedance. And it's also easy to manage because of the low impedance. So again, in summary, we have a half wavelength piece of wire right at the dead center, which is a quarter wavelength in on either side. That is the center, and that is the lowest feed point impedance. So what is a balun and what is a choke? Well, first of all, before I talk about a balun and a choke, I need to talk about what is the difference and what do we mean by balanced and versus unbalanced. So I have a little analogy here. I always like to use these little scales. I figured this is a good way to understand the difference between balanced and unbalanced. So I'm going to start over here on the left-hand side. So I show some wire here below this scale. And if you'll notice, these wires are all, symmetrical, right? There's equal wire on either side. Equal wire on either side of this down here, this ladder line. There's equal wire on either side of this cord here. And there's equal wire even here on this zip cord. So what do I mean by balanced? All of these lines that I'm showing underneath this scale are known as balanced feed lines. We can use these wires as feed lines, and these are balanced feed lines. So what makes these balanced? Why are these balanced? Well, they're balanced because they're equally spaced apart from each other. And in layman terms, what I like to do is just say, imagine taking this piece of wire right here, this entire length. And when I say the wire, I mean the wire that's actually carrying the signal. So in this case, it would be this wire and this wire. Or down here, it would be this wire and this wire. Or over here on this TV twin lead, this 300 ohm TV twin lead, it would be this wire here on the right and this wire on the left. Those are the wires that are carrying the signal. And if you could imagine peeling the plastic off of these wires and just taking the copper and placing one piece of copper in one side of this scale, place this piece of copper in the other dish on this other side of the scale, that scale will be balanced. There's equal amounts of copper on each side. That scale will be balanced. And that would apply to any one of these wires. This one right here, even this ladder line down here, there's equal amounts of copper on each side. And that is just a quick and easy way to visualize what a balanced line consists of. So anything that is balanced, just think of it this way. It has equal amounts of wire or copper, equal amounts of surface area on either side. All right. So over here, I show a scale that's off balance. So these are unbalanced feed lines. The most common is coax. So if we use our little copper analogy, we can see the difference. I have a piece of coax here, which shows the outside shield of the coax. That's a lot of copper. The copper is going all the way around the outside, a large diameter. And then I have this little piece of copper wire in the center. So if I were to take this little piece of copper wire in the center, take all the insulation off of it, put it in one side of my scale, and then I take all this shield off, which visually you can see here, there's a lot more copper on this outside, and you put it in the other dish here on your scale, you're going to see the scale is going to be off center. So that is an unbalanced feed line. That's just a quick and easy way to tell the difference between a balanced and an unbalanced feed line. And that also applies to antennas too. Here's cable TV coax, same thing applies, it's coax. This is a spool of coax used for amateur radio. Same thing applies, it's coax. And this is coax. So coax is generally referred to as unbalanced feed line, and parallel line, open wire parallel line, whether it's a ladder line or twin lead or even zip cord, that's a balanced feed line. That can be used for balance. That's a balanced conductor. Two pieces of wire equally spaced and equal amounts of copper. All right, so we established that. So I have a question. Is a dipole a balanced or unbalanced antenna? So that diagram I showed you earlier of the dipole antenna. Now I'm just talking about the antenna, not the feed line, just the antenna. A dipole is actually a balanced antenna because it's fed exactly in the center and there's equal amounts of wire on either side of that feed point. So a dipole is a balanced antenna. So what is a balun? Well, a balun is a device that converts a balanced circuit to an unbalanced circuit. So it's not pronounced balun because you don't say it balanced. At least we don't hear in America anyway. I'm not sure of anywhere else in the world if that's pronounced balanced or not. I'm not sure. But a balun is a device that converts a balanced circuit to an unbalanced circuit. And that's why it's called a balun. You can see that here. The word is made up of parts of two different words. So the most common balun that we are used to seeing is our TV adapters here for television antennas. So you can see here, I have a coax connector on one side, then I have a little cocoon, and there's a little transformer inside of here. And then I have twin lead coming out the other end. So this twin lead is a balanced feed line. It's two parallel wires, equal amount of copper on each side, right? And this is a coax connector, which has way more metal on the outside than it does on the center pin. So this is a balun. It converts a unbalanced circuit here where the coax plugs in and converts it over to a balanced circuit. This is a different over here on the right, the far right. This is the same type of transformer, but just laid out a little bit differently. This one has screw terminals, but this is a balanced output where the screws are, and this is an unbalanced output where the actual coax connector is. And then in amateur radio, when we're building HF antennas, here's an example of an MFJ balun. Same thing applies. We have a coax connector here at the bottom. That's unbalanced, more metal on the outside than the center. And then we have couple eye hooks here, eye bolts that our dipole would be supported by. And then we have two balanced pieces of wire coming out of the top of this balun. And that's what these wires is what we use to connect to each leg of our dipole antenna. Now you'll notice here, this one says 4-to-1, and it's a current balun. So let's continue talking about baluns. This picture, by the way, here, this is a choke, and we're going to talk about that in the next slide. So I pointed out something here on this balun here. I said it's a 4-to-1. So the job of a balun is to, number one, the balun has two jobs. Number one, it converts balanced to unbalanced. And its second job can be used to transform feed point impedances. So what do I mean by that? Well, down here in the bottom left corner, I show some examples. So you heard of the terms 1-to-1 balun. Well, what does that mean? Well, 1-to-1 means that if I have 50 ohms impedance on one side of the balun, the other side's also going to be 50 ohms, and that's a ratio of 1-to-1. All right. So I mentioned earlier our coax cable. A coax is a common wire we use for feed point to antennas. Coax generally is about 50 ohms, unless you use the cable TV coax, which is 75 ohms. But coax is 50 ohms, and coax is 50 ohms. So a 1-to-1 balun, for example, would be 50 ohm coax connector here on the bottom. And then on the balance side of this balun, it would also be 50 ohms up here on the top. So this balun here, let's just pretend that this balun is a 1-to-1 balun. It would convert balanced to unbalanced. And the ratio of conversion would be 50 ohms to 50 ohms, or 1-to-1. So what's a 4-to-1? Well, 4-to-1, just do the math. 200 ohms to 50 ohms. Well, what's a 9-to-1? A 9-to-1, which I don't have listed here, would be 450 ohms to 50 ohms, and so on and so forth. And you can have up to, I built a 49-to-1 balun, which converts 50 ohms to 2,450 ohms. So depending on what you're going to use that balun for, you're going to want to pick the balun with the right ratio. Okay. And then finally, one other thing I want to talk about baluns is you can get two different types of baluns. You could build two different types or buy two different types. One of the types is a current balun, and one of them is a voltage balun. And there's questions, well, what's the difference? Well, a current balun, just real quickly, tries to force equal amounts of current out on each leg of the dipole, or antenna. I should just say antenna. So a current balun would force equal amounts of current, or amps, out on each leg of your antenna. A voltage balun does the same thing, but opposite. A voltage balun is going to try to force equal amounts of voltage out on each leg of your antenna. So that's the major difference of a voltage balun or a current balun. So if you had a choice whether to use a current balun or a voltage balun, I would choose a current balun. Why? Because a current balun seems to provide better balance. Current balun generally has lower loss, depending on how they're constructed, but has lower loss. And a current balun also tolerates impedance variations better. So if your impedance is changing, different things going on, you're changing bands, so your impedance is going to change on your antennas depending on what frequency you're on. The current balun can handle that a lot better than a voltage balun. So that is my explanation of baluns. So what is a choke? In this picture here, I show where you would actually apply a choke, and it would be right on the coax itself or right on the feed line itself. So a choke is a device that chokes off or stops the flow of alternating current, AC current, on a wire or on a conductor. So in antenna systems, an RF choke can be used to prevent radio signals, stop radio signals from traveling along an unintended path and into the radio station or into your shack or on your radio. So here's a little idea of how you would build a choke. Some people can build chokes using just coax, just looping coax in a loop. And the more turns you have a coax, the more impedance more inductance that choke will develop, and as a result, the more choking it will do. In this example here, they actually put these ferrite donuts on this choke, and by adding ferrite material to a coil, you're going to increase the inductance significantly, and this choke will actually work a lot better with the ferrite on it than if you were to build the exact same choke without the ferrite, and it would operate more effectively at lower frequencies. So where would I put the choke? Why would I put a choke on my feed line? Okay, well, let's study this little antenna here for a second. So here's a dipole antenna. Remember, equal amounts of wire on each side, fed right in the center. Remember, we established earlier that this is the low impedance feed point roughly 50 to 70 ohms, somewhere in there. And we have a 50 ohm coax coming in here. And I got to make a couple statements up here before we discuss what's happening here. So we talked about balanced and unbalanced circuits in the previous slide. So we must connect balanced systems to balanced systems. So balanced circuits should always be connected to balanced circuits. Unbalanced circuits should be connected to unbalanced circuits. Whenever you mix the two, in other words, if you have a balanced antenna and you feed it with an unbalanced feed line, now you just throw the whole characteristic of balance and unbalance off. You just throw everything out of balance. So whenever you mix and match balanced and unbalanced, you start developing some problems. So this antenna, you can see this is we established earlier that a dipole antenna is a balanced antenna because there's equal amounts of wire on each side of the center, but then the coax is unbalanced. So what do we have going on here? We have a balanced antenna connected to an unbalanced feed line. And as a result, which without getting into all the math and the reasoning for this, as a result, current starts to flow down the outside of your coax here in this example. And that current will flow down, that RF current will flow down the outside of your coax all the way back to your ham shack and all the way back to the radio. Once that, eventually that coax is going to plug into the back of your radio, and it's going to just cover your whole radio. The chassis of the radio is going to have RF on it. The coax is going to have RF on it. The coax is in the house on the way to the radio. It's going to have coax. It's going to have RF on it. So a choke could be applied right here as an example to stop that current, that radiating current, from flowing down the outside the coax. And once that radiating current sees this choke, it stops dead in its tracks, and then you don't have that current afterwards. So that is an application for a choke, to prevent radiating current from traveling all the way into your ham shack. And whenever you have current flow, you have radiation. There's current flow here on the antenna, you're radiating a signal. If you have current flowing on the outside of your coax cable here, this coax is now radiating a signal. And I made a comment earlier that antennas radiate signals and feed lines are not supposed to radiate signals. But whenever you have current flowing on your feed line, you're going to start radiating a signal. And you can actually correct that or stop that or try to prevent that using a choke. So that's what a balun and a choke does. Now I know there's going to be questions afterwards, and we'll discuss that as a group after the presentation. So let's test your knowledge based on everything we learned so far. So which one of these two antennas is designed correctly, the left or the right? Now, I just established some rules in the previous slide, so the answer to this should be pretty easy. Both of these antennas, just the antenna part itself, the horizontal antenna part, is a balanced antenna. This antenna here has 51 feet on one leg and 51 feet on the other leg. This antenna over here on the right has a quarter wavelength on one leg and a quarter wavelength on the other. So now we established that this is a balanced antenna. So now what are we feeding that antenna with? This antenna on the left, we're feeding this antenna with parallel line or ladder line. This could be known as ladder line. And ladder line is a balanced feed line. There's two equal amounts of wire on each side of this feed line. So this is a balanced antenna connected to a balanced feed line. So that is correct. Over here on the right, we have a balanced antenna connected to an unbalanced feed line, which is coax, because there's more metal on the outside of the coax than there is in the center. So that's an unbalanced feed line. And as a result of mixing balanced with unbalanced, it throws the balance of the whole circuit off. And now as a result, we start getting RF current, radiating current flowing down the outside of the coax. Will that still work? yes, it will still work. It'll still radiate a signal. You'll still get out. People will still hear you and you'll still be able to make contacts. But a system like this, where you're mixing balanced and unbalanced, could cause some problems. You could start having TVI or start getting RF into certain circuits in your house, or RF on your chassis, where you put your mic up to your mouth and you get a little shock. So we'll discuss that in a little bit more detail when the questions come up after the presentation. So finally, the second question is, what can be done to fix the error in this design? In other words, how do we stop the current from flowing on the outside this coax? There's two things we can do. We can either put a balun here. Remember, a balun transforms a balanced circuit over to an unbalanced circuit. So we could put a balun there and that would help eliminate that current. And also we could add a choke. And if we were to put a choke here, just like we showed in the previous slide, it'll actually stop that current also. Or we could add both for extra precaution. All right, so let's move on. So wire antenna formulas for building your own antenna. So this is just real simple. Here's a little chart I found. It shows the major bands on HF, 160 meters all the way up to 10 meters. And it shows the rough estimated length for the total length of the antenna on each band. So for instance, on 40 meters, if I was building a half wavelength antenna for 40 meters, 7 megahertz, it would be 68.5 feet long, or 21.1 meters long. Okay, now let's look at this. 7 megahertz is 40 meters, and the antenna is 21 meters. So this antenna is about a half of a wavelength of 40 meters. And if you follow this chart all the way up, you'll notice it's very close all the way up. All right. If you want to build an antenna for an exact frequency, you can use these formulas over here on the left. So I have both of the formulas here. North America, we build our antennas. We use, we use the feet, inches, and in Europe and Asia, they'll use metric. So I have the formula for both. So if you were to cut your half wavelength of wire in feet, you would use 468 divided by frequency. If you were going to cut your length of wire using a metric tape measure and measuring in meters, you would use 142.5 divided by frequency. So we're going to come back to these formulas here in a little bit. So let's visit two common wire antennas. First, let's discuss a couple of these. So first of all, I want to talk about the G5RV antenna. So I just have some brief history here, not a lot, just real brief. And Louis Varney, G5RV is the ham who invented this antenna in 1946. The G5RV antenna, there's a lot of discussion about the G5RV antenna, especially in America. It seems to be very popular in America. And I've heard people talk about the G5RV antenna and say it's a great antenna. And I've heard other people say it's a junky antenna. I can't get out, nobody can hear me. And some people just think it's a junky antenna, but yet they're still making contacts. So what is really going on with the G5RV? Well, once we discuss what the G5RV antenna is, it'll make a lot more sense. So G5RV built this antenna for 20 meters. So the G5RV is actually a 20-meter antenna. It's tuned to 20 meters. It has a low SWR on 20 meters. It's resonant on 20 meters. And the antenna is designed using 3 half wavelength long piece of wire. So remember earlier I said the feed point of a dipole antenna, which is a half wavelength, 1/2 wavelength, has a low impedance feed point right deadly and exactly in the center, right dead exactly in the center. And then I also put in red, I mentioned, and every odd multiple thereof. So 1/2 wavelength, 3/2 wavelength, 5/2 wavelength, and so on. While the G5RV is actually a 3/2 wavelength antenna, and the feed point right in the center is around 70 ohms on 20 meters. So this is a little diagram of the G5RV. So let's tear this down a little bit. So we have 51 feet on each leg of the G5RV antenna. And if you do the math, this total length, 102 feet long, is 3 half wavelengths at 14 megahertz. That's how long that antenna is. So this antenna is actually resonant on 20 meters. So that's the antenna itself. It's a balanced antenna, equal amount of wire on each side. All right. It's fed exactly in the center. So technically it's a dipole. You know, there's equal amount wire on each side. It's a pole, you know, two poles, two equal poles. So it is a dipole. And then the G5RV antenna is fed with this ladder line, or this feed line. That's a parallel feed line. It's known as 450 ohm matching ladder line. You see some that are used, are built using twin lead, but it's still balanced feed line. So everything's good here, balanced antenna, balanced feed line. But what's unique about the G5RV antenna is this length of this feed line is cut to a specific length. In this example here, 450 ohm matching section, it's cut to 31.6 feet. All right, so 31.6 feet is a half wavelength, roughly, at 20 meters. So there's a certain characteristic, and I don't want to get into this too deeply because this is a basic introduction to wire antennas. But I mentioned earlier that feed line has certain characteristics every half wavelength. And this applies to coax, this applies to twin lead, this applies to 450 ohm ladder line, doesn't matter. For every half wavelength long, whatever frequency you're at, whatever the impedance is here, say for example, 70 ohms, a half wavelength later, it's going to be 70 ohms down here also. All right. So this on the G5RV is basically just a transformer or a matching section that mirrors this 70 ohm connection up here down to here, 31 feet later. And then at that point, we connect with a coax. So earlier we talked about what happens when you take an unbalanced feed line, coax, and connect it to a balanced antenna system. It's going to throw the entire balance off. And you can buy G5RVs that go directly from ladder line right to coax. And as a result, it just throws everything off, and the coax is radiating RF. This ladder line is radiating RF because everything's off kilter. So how you can prevent that from happening is you can put a balun here at this transition point. You can put a choke at this transition point, or both. And that will stop that radiation, and it will help transition a unbalanced circuit to coax to a balanced circuit ladder line. So this is technically how you should build this antenna, is you should have some sort of balun, choke, or both combination at this feed point to prevent that from happening. All right, so that's the G5RV. Well, it just so happens that the G5RV tunes pretty decently from 80 meters up to 10 meters. It was designed for 20 meters, but if you go down to 80 meters, it actually tunes up pretty good. It's a little bit short for 80 meters, but it tunes up okay. And it'll work okay on 40 because it's long enough for 40, no problems, all the way up to 10 meters. So the G5RV actually is not a bad antenna. It might be a little short for 80 meters, but in general, it's not a bad antenna if you understand why it was built and how it's built and what it's for. Now on 20 meters, you could probably use this thing without a tuner at all because it's actually designed for 20 meters. Okay, I also want to talk about the off-center fed antenna. So what is unique about the off-center fed antenna? Why are we going to pick an off-center fed antenna as opposed to a dipole? Is an off-center fed antenna a dipole? By definition, no, it's not. A dipole has equal legs or equal poles on each side. 2 equal poles, dipole. This really technically is not a dipole because it's fed over to the side. So why is this antenna fed over to the side? Why am I feeding it there and not the center? And what's going on here? So let's start with the basics. What do we know? We know that when we're building an antenna, we want a half wavelength piece of wire. 2/3 plus 1/3 equals a complete, 1. This is 1/2 wavelength of wire. Same length as a dipole. However, instead of cutting the wire in half and feeding it exactly in the middle, I folded the wire and I cut it 1/3, 2/3. Okay. So I want to make a point here. You still have a half wavelength of wire hanging up in the air. It's still a complete antenna, but you can feed that half wavelength piece of wire anywhere. You can feed it in the center. You can feed it 3 feet over to the side. You can feed it at 1/3, 2/3. You could even keep going and feed it over here someplace. You can feed it anywhere. It's still, at the end of the day, it's still a half wavelength piece of wire, but you're just feeding it in a different spot. And depending on where you're feeding it, the impedance is going to be different. And we'll talk about that in more depth during the discussions after the presentation. So we established that the off-center fed is still a half wavelength piece of wire from end to end, except it's fed on in the center. It's fed off center, 1/3, 2/3 over on the side. Doesn't matter which side. And what's unique about this feed point, we talked about earlier, dead center right in the middle. That's 50 ohms, 50 to 70 ohms, very low impedance. Well, as you head toward the other end of this antenna, no matter which direction you go from center, if you start going east and you start going to this end of the antenna, or you start going west and you start going out to this end of the antenna, it doesn't matter. As you leave the center of this piece of wire and you start going out toward the end, the impedance starts increasing. And roughly around this ratio, somewhere in here, 1/3, 2/3, that feed point resistance or impedance is 200 ohms. So in the center, remember it was about 50 to 70 ohms. Well, now out here, 1/3, 2/3, it's at 200 ohms. So what's going on? Well, now I have a 200 ohm feed point. I'm still using 50 ohm coax. So what do I have to do? I have to put a bell in here to convert 200 ohms to 50 ohms. What's the ratio, the impedance ratio of the balun I'm going to choose? It's going to be a 4:1. 50 goes into 200 4 times. So 50 ohms on this side, 200 ohms on that side, that's a 4:1 balun. And I'm going to choose a current balun because I mentioned earlier, current baluns, I just, they seem to work better, and I just like current baluns way better than voltage baluns. All right. So now the question is, well, what kind of balun do I use? A 1:1, 4:1? Well, we just figured out this has to be a 4:1 for it to be the most effective, because we have 200 ohms here and we have 50 ohms here. What's unique about this antenna, and the reason it's fed off center, is I built one of these antennas for my place. And the reason I chose this construction is because I noticed that no matter what band I use this antenna on, if it's 80 meters, I build it for 80 meters, and I go to 40 meters, I go to 20 meters, I noticed that this impedance right here doesn't really change much. It's always hovering right around 200 ohms. It changes, it goes up and down a little bit, but it's always around 200 ohms. So I get a pretty good match on 80 meters, 40 meters, 20 meters, 15 meters, 10 meters. all the resonant bands. And why I did this instead of going with my dipole is because my automatic antenna tuner in my radio handled the tuning of this antenna much better than when I was feeding it in the center. And when we get into the discussion after the presentation, we can talk about what's happening there and what causes that. All right. So that's why this antenna is popular, is because this antenna works well. It has a relative low SWR in most of our common HF bands. So our internal tuners can handle the tuning of this antenna. All right, so that's the reason for the off-center fed. Now you can keep moving this out and you can find the sweet spot, because it might not be exactly 1/3, 2/3. It might be a little bit further over depending on your environment, you know, based on how high it is off the ground, your tree cover, you know, different things like that. So it's something you can play around with a little bit. All right, so we're getting toward the end here. So building your own wire antenna. So I just put together a quick step here, a step-by-step on what to do to build your own antenna. So first of all, you have to determine what is your lowest HF band that you're gonna use. Is it 80 meters? Is it 160 meters? Or maybe it's just 40 meters. So what you want to do on HF, if you're going to build a single wire antenna for HF and you want to use it on multiple bands, I would suggest you build it for the lowest band that you're going to work with. So if the lowest band you're going to get on is 80 meters, which is 3.5 megahertz, then build that antenna for 3.5 megahertz. Then once you determine that, using the formulas, you cut the wire to the length for the lowest frequency. So you take the 468 divided by 3.5 megahertz and you calculate that out. You cut the wire, one single piece of wire for that length, however many feet that will be, like 130 feet or whatever, 133 feet. Okay, now you have a single, solid, unbroken, half wavelength piece of wire. Now you have to decide, number 3, how to feed that wire. Are you going to feed it in the center and make it a dipole? Are you going to feed it off center, make it an off center fed, or somewhere in between? You have to decide where you're going to feed that wire from, or are you going to feed it at the very end and make it an end fed antenna? So you have to decide where you're going to feed that antenna before you cut the wire in half, or cut it in whatever ratio you're going to cut it. Then finally, once you determine that, you cut the wire at the feed point. You connect your feed line to the antenna. You can use coax or twin lead. And then you would use a balun and choke when necessary to make that transition when you connect your feed line to the antenna. So again, this is the formula. Calculate antenna length for imperial. It's 468 divided by frequency. That'll give you the length of a half wavelength of wire. And 142.5 divided by frequency, and that'll give you in meters the length of wire you would cut. And I can explain if somebody has any questions, how did they come up with this number? But anyway, that's the formula you would use. And here's a chart that shows you just real quickly, roughly what the length's going to be. So it looks like 137 feet long at 3.5 megahertz, all the way up to 10 meters. And then when you're done, you hang the antenna up. And finally, you get on the air. Now, hopefully you don't have this problem with the TVI, but this is your end result here. So in conclusion, let's review our presentation outline. We discussed and went over the initially some definitions. And we talked about the anatomy of a ham radio dipole antenna. What is a dipole antenna? And we We also discussed why is it a half wavelength long and why do we feed the dipole in the center. We discussed what a balun is and what a choke is and what its purpose is. But first, before we did that, we had to establish the difference between balanced and an unbalanced circuit. We went over the wire antenna formulas. We visited two common wire antennas, the G5RV and the OffCenter Feed antenna. We discussed about building your own antenna. And we're at the end of the presentation. And then after this, we're going to have a discussion afterwards. And I'm sure there's going to be a lot of questions. So now, at the end of this presentation, you should be able to identify the components of a dipole antenna, explain the purpose of a balun and a choke, use the formulas to build a wire antenna for yourself, convey the construction methods of a G5RV and the OffCenter Feed antenna, and finally build an effective wire antenna for HF. All right, so I want to thank everybody for your participation, and now we can open up the mics for discussion.
Great job, Paul.
So are there any questions? Anybody? I know there's a lot of new hands here too. So I see Gary. Now I can't see. Can I see everybody? Let me double check. Oh, wow, 44. So I see Gary, you had your hand up.
Yeah, what is the proper method of grounding the center fed dipole?
Grounding. So
Yeah.
So we talked about the center fed, you know, the dipole is just by definition center fed. So if you were to ground the dipole itself, I'm just trying to establish something here. So if you were to actually run a wire up to the dipole itself and ground it, what would happen to that antenna? You would throw it off balance, right?
Okay.
It's no longer going to have equal amount of wire on each side. So what I would do is I would build the antenna. I would put a balun at the transition point, you know, where the feed point feeds the antenna. And then right before the antenna comes in the house, what I do, before the coax comes into the house, I put a choke right there to choke off any RF prior to it, to the feed line coming into my house. And then I would ground the shield of that coax after the choke, not on the antenna side to choke, but on the other side. Well, let me think here. Yeah, on the other side to choke, on the radio side to choke. That's where I would put my ground.
Okay, thank you.
I have one, Paul.
Okay, go ahead. And by the way, there's others here that have experience with this too. So please, you know, just, you know, jump in here and tell us what you've done, or, you know, I'm not an expert at this. So just please, anybody pop in. Go ahead, Dave.
We talked about this yesterday, and if this is getting too techy, I know this is antenna 101, but can you touch on the difference, the change in impedance as the dipole gets higher away from the ground? Or is that getting too techy?
Well, so here, let me show. I got some extra slides here. No, I didn't discuss the whole thing of the antenna being too close to the ground, and I'd have to look that up. But what happens is when the antenna, so what happens is the radiation pattern is going to change. So if the antenna is very close to the ground, and when we say close, we're referring to distance and wavelengths. Okay, so on 80 meters, a wavelength is 80 meters long. A half wavelength is 40 meters long. So if you convert that to feet, and I'm just roughly converting it to feet, 40 times 3, that's about 120 feet. So if the antenna is closer to the ground than a half a wavelength, it starts to skew the radiation pattern. And if the antenna, and most hams, they can't get their antennas up that high on 80 meters, for example. So the closer the antenna is to the ground, the radiation pattern, I know this wasn't your question, but I'm going to talk about this anyway. The radiation pattern will be more in a straight up configuration. Basically, it'd be like If you were in a room with a mirror on the ceiling and you had a flashlight and you shine the flashlight straight up, it's going to come straight back down and hit you right in the face. And then as you raise that antenna further and further away from the ground and get it up higher, 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 the lobes, the radiation lobes of that antenna will start to go out toward the horizon more and more and more the higher you get it up. And it'll become a better antenna for working DX. Well, also when you put the antenna really close to the ground, it's going to change the length of your antenna electrically, and it's going to change the impedance a little bit. So for instance, if you have an antenna way up in the air and you cut it to a certain length and it's tuned to a certain frequency, and the SWR is really good at a certain frequency, say 3.5 megahertz, and you take that same antenna and bring it all the way down, and I'm going to go completely ridiculous, bring it all the way down and only have it 2 feet off the ground, you're going to notice your tuned frequency is going to change. And you're going to have to shorten that wire, I believe, to get it back on frequency again. I think that's, yeah, I'm trying to think. So what happens is your impedance is going to change, your velocity factor is going to change. There's a whole bunch of things that change.
Okay,
But,
that goes into antennas 102. Thanks, Paul.
yeah, okay. Also, but I want to show you guys this here. Okay, there's another question. I'm going to show you guys this, but what's the next question?
I've got a question about the, you mentioned chokes and balance being optional.
Yeah.
I don't see the chokes as, I say the choke as being, you want to use a choke most of the time since it acts as a form of protection. Yes?
Well, everything's optional, right? You can build an antenna just like this right here, and that'll work fine. And people have done that and works great. You know, some people have problems with it with TVI, or, you know, they can be heard on their toaster or whatever. And other people don't have any problems at all. So you can do anything you want and it'll work. But if you want to be a purist and if you are having TVI, now you have to start looking into that. So yes, it is optional. Everything is optional.
Yeah, I would lean towards using a choke.
Okay.
On the other hand, with the balun, I wasn't too clear on it, other than the example that you gave about a half wavelength long ladder line where it would transform or maintain the impedance at the feed point.
Oh,
Other than that, I wasn't too clear as to when you would use a balun.
okay. So that's a common question. So when do I use a balun? When do I not use a balun? Well, I'm going to go back to this picture right here. Okay. So I could build an antenna like this. Now, let me ask you, is this just looking at the antenna, not the feed line, is this a balanced antenna or an unbalanced antenna?
Balanced.
Okay. Is this a balanced antenna or an unbalanced antenna?
Unbalanced.
No, just the antenna. Just the wire.
Oh, balanced.
Balance, correct. Okay, now this is twin lead. So this is ladder line. So I'm taking a balanced antenna, feeding it with a balanced feed line all the way down and into my shack. Okay. And that's fine. And that'll work fine. But then on the other end where this plugs into the radio, you have to have some sort of balun to convert that unbalanced or this balanced network over to unbalanced. Why? Because on the back of your radio, what kind of connector is that? Is that balanced or unbalanced on the back of your radio?
Unbalanced 50 ohms.
Yep. So that's where you would have to eventually use a balun to convert that over to unbalanced circuit.
Okay.
Now, what if you didn't use a balun? What if you just stripped these wires, stuck one wire in the center conductor of your coax, stuck the other wire on the shield? What would happen?
You'd be at the mercy of the length of that feed line, I guess, as to what the impedance was.
Yeah. So
And
what
then you
happens? So what happens?
You have a mismatch.
Right. You'd have a mismatch in balanced versus unbalanced. Okay. This would be a perfectly balanced antenna. Perfectly balanced. It's a nice sunny day. The birds are chirping, da 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 da. And all of a sudden, you hook a piece of coax on the end of this without a balun, and now you just threw the entire circuit out of balance. I mean, the entire circuit. All this feed line everything.
But didn't you say if that was a half wavelength long twin line, it would be almost close to 50 to 70 ohms anyway?
Yeah, so I'm going to refer you back to the G5RV antenna, and now I understand where you're coming from. So
Yeah.
when I say balanced versus unbalanced, I'm not talking about 50 ohms versus 200 ohms. Okay, so ignore this part down here. See where my mouse is in the bottom left corner?
Mm-hmm.
The balun, its main job is just to convert balanced to unbalanced. That's its main
Okay.
job. That's it. However, because the way they're built, they're basically transformers. They also have another characteristic, and they transform impedances. Okay, so the main purpose of a balun is just to convert, because it's in the name of the balun. It converts balanced to unbalanced. That's the main purpose of a balun. That's it. If there's one thing you can remember or take away from this slide, is don't forget that a balun converts balanced to unbalanced.
Okay.
Even if you ignore this whole impedance thing down here, just remember that one thing. That's when you decide. So the question is, when do I use a balun? When do I not use a balun? Would you use a balun in a balanced circuit?
No.
No. Would you use a balun when you have a balanced circuit here on the top and an unbalanced circuit here on the bottom? Would you use a balun then? Say yes.
Yes. Yeah.
And do you understand why?
Yeah, you're going from an unbalanced feed point, a feed line, to a balanced antenna.
Yep, exactly. So that's answers the question. When do I use a balun? I use a balun when I'm converting or transitioning, that's a better word, when I'm transitioning from an unbalanced circuit to a balanced circuit.
Mhm.
That's when I would use a balun.
Okay.
Okay.
I don't want to take up too much time. Thank you very much.
Okay. I hope I'm answering the questions okay. Any others? I'm going to point something out here too. This is something I had in my original slides, but I took it out. Hey, Dave, you like how I did this with my rabbit?
I love it. Yes.
I got TV.
I like Homer too.
Okay, so this is something I want to point out here, but I took it out of my main presentation and I brought it out here. So there was a question one day that why can I feed a half wave length of wire at the end? And somebody asked, I'm going to ask this question. If I have a halfway, and anybody answer it, I can't see you guys because I'm looking at my presentation. I only have one monitor. So if I have a half wavelength piece of wire, okay, end to end, it's not cut or anything. It's just one solid piece of wire. My question is, where can I feed that wire? In other words, where can I hook my feed line to that wire? Anybody?
Anywhere.
Anywhere, exactly. That's where that was the answer I'm looking for. So if I hook it in the center, that's the low voltage point, which results in a low impedance point. So, 50, 70 ohms, somewhere in there. Basically, it's the same impedance as my coax. Okay. If I go out and I start heading out in either direction, doesn't matter, I'm heading out to the end. Theoretically, when you get to the very end of your wire, it's infinite. The impedance is infinite, but in real world, because this is the real world, it's several thousand ohms. It could be 2,500 ohms. Okay, could be 3,000 ohms. I don't know, whatever, somewhere in there. And again, it depends on how high it's off the ground and the angle that it's pitched, and a whole bunch of stuff, surrounding material. Okay, so as you see, this is the lowest point, 70 ohms, and as I reach and head out toward the center, out toward the end, I get somewhere here about 1/3, 2/3 roughly, and that's 200 ohms. And I keep going, and it's 300 ohms, 400 ohms, 800 ohms, 1,000 ohms, 1,200 ohms, and it just keeps going up and up. And eventually you get to the end, and it might be 3,000 ohms or 2,500 ohms. Can I feed my half wavelength of wire on the end? Yes or no?
Yes.
Yes. But what's going to be hard to deal with on the end? These
The,
several thousand ohms, that's going to be hard to deal with.
Balun.
So then we would use a balun. And the reason we're using the balun there, now this is going to be confusing because I'm going to contradict myself. The reason why we would use a balun there is to get that impedance transformation, that, you know, to go from 50 ohms up to 2000 ohms. So if I were to use an end-fed wire and I were to feed it out here, say I cut the wire for 80 meters and I feed it way out here and it's 2000 ohms, say 2400 ohms, and I have a piece of 50 ohm coax, what's the ratio I would use to get that as close as possible?
9-1,
I'm gonna say 49-1.
49-1,
49-1.
9-1.
Okay, so how do I determine that? Take 49 times 50. And it comes out to 2400 ohms. So yes, you would use a 49-to-1 transformer out here, or balun, to convert that 2400 ohms on the end of this wire to your 50 ohms on your coax. Does that make sense?
It does
Now-
to me.
So now you understand what that, you know, those different ratios are for?
Question.
Yes, go ahead.
Okay, when you have a dipole antenna, it's resonant on every third harmonic. But when you use when you take that same quarter wavelength of wire and you feed it at the end, it becomes resonant on every multiple on every harmonic. What happens there? How does that work?
Okay, I'm gonna see somebody else jump in there at the same time if they have any. I'm gonna start this and then somebody else jump in if they can help answer this question. So let me go back to a simple dipole diagram here somewhere. How about that one? I mean, it doesn't matter, I guess. See if I have a better one. There we go. We'll do this. Okay, so if we have a dipole, we have a half wavelength of wire. We cut it in the middle. Now we have a quarter wavelength here and a quarter wavelength here. But at the end of the day, we need a half a wavelength for efficient radiation, okay? So if I took only a quarter wavelength piece of wire, you know, I cut the dipole, I cut this wire in the middle, I throw this piece away in the garbage, just get rid of it. And now I just take a quarter wavelength and I feed that to my radio, okay? Now I only have half an antenna. And in order for this to work effectively, and I don't know how to explain this exactly, so maybe somebody help me out. But in order for this to work effectively, the circuit, you know, if you can kind of picture the circuit like being alive or whatever, the circuit is going to seek out for that other half to make it a complete half wave. So if you had a piece of coax coming up here and you only hook the center conductor up to this wire here and this wire's gone, you know, you threw it away. It's a quarter wavelength long. That circuit is going to want to complete itself. And it's going to start using the outside shield as your coax as part of your antenna. Because it's going to try to find that other quarter wavelength to get the entire half wavelength. So for example, if you're on a car and you want to put a quarter wavelength whip on your car for 2 meters, it's only a quarter. Where's the other half? Well, the other half is the chassis of your vehicle. It's using the chassis of your vehicle to make a complete half wavelength antenna.
Well, Paul, wouldn't that when the end fed comes in where you run a wire to ground, put a ground rod in and put a 9-to-1?
So you can do that. You can run a wire to ground, but you have to have another half someplace for it to effectively radiate. Now here's a problem. So, okay, I cut this entire piece of wire right here to a half wavelength, say on 40 meters. Okay, so this whole piece of wire unbroken is going to be, what is it going to be for 40? 60 feet long, let's just say, you know, just rounding up. Okay, so on 40 meters, this is a complete half wavelength piece of wire, right? Okay, what if I decide, because I don't have the room, hey, I got a 40 meter piece of wire up, I'm feeding it on the end, And I decide I'm gonna see if this thing will tune up on 80. So then I go down to 80 meters. Now how long is this wire? Is it still a half wavelength? No, it's a quarter now because you went down in frequency. So now this is only a quarter wavelength on 80 meters. So that'd be the same thing as that quarter wave, that end-fed quarter wave antenna. Well, now in order to complete that antenna, you got to find another quarter wave someplace. So then you would have to find it, say, on your tower, you know, whether it's the ground on your tower or, you know, the shield in your coax or something. It's going to seek out that other half someplace. Does that kind of make sense? I mean, I don't know if that was confusing or not. I'm not sure. Did that answer your question? Kinda? No?
That made sense to me because I put some quarter wave slopers up on my tower, and the first time I keyed my radio, it looked like Christmas down here on all my antenna switches and everything, because all that RF was back feeding. So what we did is we went back up the tower and built some ugly balance and stuck on there, and that solved the problem on that.
Yep. So what you essentially did, Scott, was you took a quarter wavelength of wire, you put it on your tower, and you ran your coax. I'll just say I've done this before. Ran your coax up to the top of your tower, hook the shield of your coax to your tower, and then you hook your center conductor up to that quarter wave. And then it's going to use that tower kind of sort of as the other half of that antenna. But also it could use the shield of your coax also at the same time. And then that RF comes down your shield, comes into your shack, and now it's lighting up everything in your shack and sparking on your mouth, you know, when you touch your mouth on the mic. So how you can prevent that from happening is you can, like exactly what you did, is put a choke on your coax so that RF doesn't follow your coax and only follows the tower. And you can stop that RF from going down your coax on the shield. So that's a perfect application of a choke.
Right. Yeah, we also built a RF little sniffer here too, and so keep that in the shack so I know if there's any stray RF in here. Also, I've been experimenting with off-center fed dipoles too. I've been running about 35 feet in the center and 10 off the ends, and I'm pretty impressed. Except it doesn't work on 15 meters. It's not in the right harmonic there for it. But other than that, man, it's a awesome job.
Yeah. Yeah, and I noticed they don't tune up on every band. I have to use a manual tuner, you know, to get on the other bands that they don't exactly. Nothing's perfect, right? Unless you stick a dummy load there. But yeah, cool. Any other questions?
Well, I was just going to say some of the tuners. Now, I recently just bought a tuner, a used tuner, and I know we were talking to Tom. On the back, that tuner will take open wire. You don't see that much anymore. In the old days, you used to see it a lot. Back in the 50s, and used to see a lot.
So here,
People, I think because
that.
people couldn't afford coax. Coax was, you know, in the 50s, I don't know when coax come out, but in the 50s, coax was
expensive. Yeah.
expensive. Exactly.
And people
And
made their own.
all the old timers ran open wire.
Yeah, people made their own too. Just two pieces of wire and wooden dowels in between, and it looked like a ladder. Like it looked like one of those ladders you throw out your window to escape from a fire. I was going to make a comment about, okay, so imagine using open wire or parallel wire feed line, like twin lead or something, and coming into the shack with that and going right to your tuner. So what's the problem with doing that, especially nowadays?
Talk about bringing RF into your shack.
Now, so the feed line technically is not supposed to radiate, right? So if you have a balanced antenna and you have balanced feed line and everything's balanced, the feed line should not radiate at all. What causes the feed line to start radiating? If you have a balanced antenna feeding it with balanced feed line, when does that balanced feed line start to radiate? When
Connection to the radio.
Yeah, when it no longer is balanced, right? When it loses its balance, how does a feed line, when you have two parallel wires coming down, how does that wire lose its balance?
When it's changed to anything but balanced.
Yeah,
Music
when
coax
it's
or
changed.
connector or,
Yeah, so when you plug it into your radio, just like Bob said, or, but another thing where I was headed with that is, what if you come into the house and you happen to have a water pipe right there? And that feed line goes right by your water pipe, or right by one of your electrical wires, or one leg of that feed line is closer to the water pipe than the other leg. Now you just threw that whole thing off balance. So that's why it's hard to deal with that in the house, because once you come in the house, you got heating ducts in the house, you got wire, you got copper pipe, and it's really hard to keep it away from metal once you come into, you know, one of the modern day houses now. So what I did is I would feed line, you know, parallel feed line as far as I possibly could. You know, I have aluminum siding on my house. So right before I went into the house, I would put a balun right at the bottom and then convert it to coax right before it went in the house. So I mostly had open feed line for efficiency, mostly, but I had to convert it before I went into the house. Otherwise I would have threw the whole balance off. So that's something to keep in mind. And that's why people have TVI when they say, oh, I don't use balance line because it causes TVI. Well, the only reason it's causing TVI is because you lost the balance someplace along the way. And feed line is not supposed to radiate at all. It's only a way of getting RF from point A to point B. And, you know, that's how TVI a lot of times gets in the house, is your feed line's radiating. It's going right next to your cable TV cable on the way to your ham shack, you know, next to your electrical wires, everything. All of a sudden your furnace heating ducts start talking when you get on HF.